All right, howdy. So this is a fun one. It's going to be fairly interesting. So what we're doing is it says we're taking this cylinder and we're cutting it into thirds lengthwise, which means we're making cuts like that all the way down to the bottom there. And then we're going to do that to a second cylinder. So we've got one cylinder here that has a mass of 3m, then another one that's identical over here. That has a mass of 6m. We're going to cut it into thirds as well, not into quarters. And then we're going to glue one of these wedges to one of these wedges. All right. And this is going to be a way to balance some torques. So it's going to be a little bit interesting that way. And, what we want to do is we want to set this on its edge so that we have this thing in thirds. This is going to be from this guy here. So 1/3 of 6m is 2m. And then this guy is going to be 1/3 of 3m, which is just m, which is the reason why I chose that. And then there's going to be a box somewhere over here that has a mass m. Okay, and the job of this problem is figuring out where to put that box there to balance this area here, which has mass. This other area here is blank. There's nothing there. So that's more or less what this is. It's a very interesting problem, I think. And, we're going to do some torques. We're going to calculate some torques. We're going to do some vectors. We might have to find the center of mass of something, because I don't know right off the top of my head what the center of mass of each one of these things is. So the general approach will be, we've got these three objects, right? This guy is considered to be very small. The box is small, so we're just going to pretend he's a point particle. But we're going to have to find the center of mass of these two guys. Now, they have the same center of mass as far as their distance from the point here is, right? So this distance is the same, but this position is different. So that's going to give us something. And then we're going to have to apply torques. The torques are going to be applied from the centers of mass because the weight is going to be applied from the centers of mass. So this guy, the heavy one, is on the left side here. He's raised up high. He wants to pull everything in this direction, in the counterclockwise direction, in the positive direction. And this other guy here, this lower wedge, this lighter wedge, wants to pull it in the opposite direction. And, it would probably end up looking something like this when it was done, right? Because it'd be somewhere on this 2m side that it would make contact if I just let this find its own natural equilibrium. But I want it to have this horizontal line here, so I put this box there. I don't know why I wanted that, other than that's what it said in the problem statement. So that's it. It's actually really interesting. I think this is a nice little problem. All right, so what do we know about it? Well, let's go ahead and give ourselves a drawing. Right, so we said we had something looking like this, right, with 2m here and m here in the box. And that's supposed to be stable. We know for wedge 1, for this guy, probably I should have called the other one wedge 1, but it's too late. Wedge 1, the mass is 2m, right, because it's 1/3 of 6m. We know the radius is r, and that's all we need. And for wedge 2, we have a mass of m and a radius r. And then we have our box, which only needs a mass, and that's m. So it's just as heavy as this guy here, so it's a heavy little box. And then we need to find something. And we need to find from the points this distance right here, so the position of the box. What should we call that? Let's call that X. Let's call that X. Let's be traditional. Okay, so now we have to try to figure out where everything goes. I did make an error, but that's okay. Let's see. What is the concept here? This is rotational equilibrium. This is the what do we call that? That is the analog to Newton's first law for rotations. Okay, so that's rotational equilibrium. That instead of using forces, we use the torques. And we say all the torques are equal to 0 in rotational equilibrium. So this will also give you stability, which is what we're looking for. But this would also be the same as if you had something spinning, right? If you had a, let's say you had a wheel that you had to keep spinning in the presence of friction, then you'd have to add, some power to it to keep it running at the same speed. All right, and then we need a representation. So I'm just going to make a circle. So in general, there are two good representations here for what I'd like to call a extended body diagram, because it's for an extended body. And in both cases, we have zero net anything, because it's going to stay still, right? It's going to just sit on the floor there, or on the table, or whatever. And then we have to figure out where do the forces go. So the forces are someplace off of the center there. So we have like a weight for 1 there and a weight for 2 in this sector right here. And then along this thing here, there's the weight for the box. Okay. So I should have kept those similar. So what we're saying is that, because of the symmetry here, because of the way this is geometrically constrained, the center of mass for this wedge is sitting there right on the y-axis. Right, this is the y-axis. This is the z-axis. Whereas this one's not. So we're going to have to figure out where that is. That's not going to be very hard. We have, geometrical constraints. This entire thing is, pi over 2 pi over 3, which means the angle here is pi over 3. This is going to make life easy for figuring out directions, right? We already know that from the geometry. So this will be basically no problem, except I don't really know what that point is, right? I don't know that formula off the top of my head, so I'm going to have to derive it. Don't usually like to derive things, but you need to figure stuff out sometimes. You can't just look things up all the time. All right, so let's start with our definition of torque. So we're going to use a definition of torque to find this position x. So we want to find it for that force, which is along the y-axis. So the torque for the box, which for some reason I called P, is equal to the position here, which is x in the y-hat direction, right? It's the y-hat direction. We don't need to worry too much about that. And times cross with the weight of the box, which is mg in the minus z-hat direction, right? So that gives us 1 torque. Let's see. Or that gives us x, and that means we need to find the torque, and we know this guy, and we're allowed to assume that guy, right? So we always know what the gravitational acceleration is. The mass is sitting up here. We want the mass for that. That's fine. Now we have to figure out some way to relate the torque on the box to other things that we need to use in the problem. Well, we already figured out a way to do that, which was rotational equilibrium. So, rotational equilibrium. And that's going to be, well, we want tau p, right? So that we've got that one. Plus we need a torque from the left-hand side, plus a torque from the right-hand side. And that all has to equal 0. And 0 is a vector 0. It's 0 in all directions. It might be a little bit pedantic to put a vector over it, but that's okay. All right, so then we have a couple of question marks there. So we have to find both of these. So let's go from left to right. We'll use the definition of torque. And that says that tau L is going to be the force from there. We don't know what that spot is there, so we'll call it y. We don't know what the center of mass is. It's y in the minus y hat direction, so it's going to the left from what I'm calling the origin, which is the places where the points meet, times the mass of this thing, which is 2m, right? 2m there, times g, times minus z hat, because it's going in the negative z direction. It's pointing what we call down. That's a technical term, down. All right, so we'll do 4 now. That I'm going to use the definition of the center of mass, because this guy here that we don't know is the center of mass of the wedge. So now we have to write out the center of mass equation. Well, that's the total mass of the wedge times the center of mass, what we're looking for, right? So we know that guy, we want that guy. And that's going to be equal to something that's going to hurt your brain. It's going to be equal to the integral over this entire area, which will be from 0 to r, right, from here to here. But it'll be from 0 to r everywhere along here, so we have to integrate from here to here and all the way around that wedge, all that way down around that third of a circle. So that's going to be minus pi over 3 to pi over 3, right? Because we want the center of mass to be right there in the center, so we only care about, it's best to set this up so that the zero's in the center. We will have to worry about some vector stuff in a second. Then we need to multiply that by the density. Now the density of this guy is its mass over its area. We know its area, right? Which is pi over 3 times r squared, excuse me. Right, so pi r squared is the area of the circle around the cylinder. We don't care about the lengthwise because that doesn't change. So we're using a surface mass density, a 2D density. So we have 2m over pi over 3 r squared, because we're only looking at that 1/3 of a circle. And that gives us that density part. Next we have the position part. Now, center of mass is technically a vector, right? So we've just set this up so that one of those components is going to be 0. Because of the symmetry, the y component or the z component of the center of mass is going to be 0. The y component is not going to be 0. So we don't have just r, we have r cosine theta. Okay, and I've already taken care of the minus sign by putting a minus sign on the y hat, so we don't have to worry about that. So this is the component of the vector r. So if we have a vector here, it's too small. So if I have a vector here, r, then this is r cosine theta. So all we care about for finding the x component of or the y component of the center of mass is the y component. We can ignore the z component, which we're saying is going to disappear by symmetry. You can do the integral yourself if you like, and you will find the same thing. So that's perfectly fine. Now this has not been too terrible so far. This is the part that you may or may not have seen before, but in cylindrical coordinates, r d theta is what you give for your theta integral. So the reason for that is both of these guys, or r d theta and dr, are integral elements in space, right? So as you get farther and farther away from the center of your circle, if you make a movement of an angle theta, right, your arc length around here and around here and around here are different. So this is r theta over 3, this is 2r theta over 3, this is just r theta, right? So this is the arc length theta times the radius, and as you get closer and closer in, that reduces in size. And that's exactly what this is saying here. This is basically talking about that. So that's just a way to work with those. You'll get to do lots and lots of that stuff in the future, don't worry. It'll make you happy. And actually, this particular integral is going to sort of break down into something very simple in just a few minutes. Let's see. They don't all do that. At some point, they give you ones that you can't just break down. All right, then we're going to go back to the definition of torque, and we're going to do that because the r's are dummy variables, the thetas are dummy variables, right? We have the d theta dr, that means we're going to integrate them out. We know all this other stuff on this side. So we're done with everything with TL, so we have to go back to TR. Okay, and TR is going to have actually the same distance, the same distance from here to here, the same distance as here to here is the center of mass. It just has a different direction. So we're going to have to figure out that direction next. We don't know what that direction is off the top of our heads. We've already found y, that's there. And we have to do the cross product to get the torque. We do the cross product with the force. The force is the weight. The weight is, in this case, m instead of 2mg, but it's still going down. Remember that word, down. Okay. You might write it in your notebook, look it up in the dictionary, find out what it means. I'm sure you've never heard it before. All right, 6. Then we have vector decomposition. Okay, so we need to break this into x and y, or y and z components. So what is r in terms of y and z components? Do you have enough room here to play with it? Probably not. Okay, so what we said was this is horizontal, and this is the center of this wedge, right? So this is pi over 3 here. So that would mean that this length here, the z component is the square root of 3 over 2, and this one is 1/2, right? This is, pi over 3 is just equal to 60 degrees, so that's 1/2, and that's the square root of 3 over 2. So we just use our well-known special angles. I don't know why they ended up being such special angles, that we know them so well. Probably because it gives you the 1/2 here. And so we just have a couple of numbers times a couple of unit vectors. This should be minus square root of 3 over 2, or, well, let's use plus and minus z. That'll be fine, because we've been doing that the entire way through. Although that's not what I did on the next slide. So that gives us everything we need. There's nothing else we don't know, right? We know the M and we know the G. I haven't seen anything else we don't know. So we're ready to go. We're almost done with this. Now, like I said before in a previous one of these things, I like to take anything that looks like it's going to be really nasty and hard, like an integral, and do that first, just so that when we get to the substitution phase, we don't have to worry about it. So for this guy, we've got a couple of things, right? First, we can cancel out those two m's because they're just constants. This guy has to get pulled out in front, right? So let's go A. I don't know how big this is going to be. Y is equal to 1 over that pi over 3r squared. And this is just simplification, actually. Let's see. Then we have the integral part. I probably should have written something out here because I've got plenty of room, actually. We've got the inner part of the integral, which is the integral from minus pi over 3 to pi over 3. The r has no dependence on theta, so it comes out. This other r does as well. So the only thing left in that integral is cosine theta, d theta. We're okay with that. And then we have an integral from, let's see, 0 to r of the other things. And theta and r are basically independent. We got rid of the dependence right there. So that this is the integral of r squared dr. And now you have two integrals that you have to do, this one and this one. And you know the answers to each one of those, right? You've seen those before. This guy, the integral of cosine theta is sine theta, right? And we're going to have to integrate that at minus pi over 3 to pi over 3. And then this guy here is just 1/3 big R cubed, right? Because it's the integral of x squared is 1/3 x cubed. So this is nothing. So when we integrate, we end up with y is equal to, I'll put the 3 in the numerator, 3 over pi r squared times, according to this, we have 2 sine pi over 3, right, times 1/3 r cubed, which is nice. We can get rid of the r squared and that cube, so that's just r. We can get rid of this 3 and that 3, right? And sine pi over 3 is the square root of 3 over 2. Right? This is the square root of 3 over 2. So we're going to be able to get rid of the 2. So we just have the square root of 3 over pi r. So that's equal to the square root of 3 over pi r. That doesn't look so hard. I mean, it's a kind of weird number, the square root of 3 over pi. But other than that, I mean, it's a simple sort of deal. So now we're going to get into substitution. So we're going to take, so I've just used A, I've used center of mass. I'm going to use B, and I'm going to plug it into the right hand one maybe, to 5. And I'll put 6 in there as well. So 6 and B go into 5. Alright, so that's going to be y, what we just found, the square root of 3 over pi r, cross mg. And this is going to be multiplied by 1/2 y hat. And z cross z is 0, so we have this guy times minus z hat. So that's actually minus x hat. So I don't know if I remember all these things. So let me see. Let's see. So my tau right is equal to the square root of 3 over pi I just said, basically times mgr, and this is going to go in the minus x direction. D, let's do another torque. Let's do the left-hand side. So let's do, don't have to do any other substitutions. We just have to put b into 3. We have minus y times minus z. So that's just positive x. And this is quite similar. This is quite similar. This is the square root of 3 over pi times 2mgr in the x hat direction. Oh, I've got the 1/2. There's a 1/2 here. Okay. Got that 1/2. Right, so now I have this guy up here. That's 2m times this thing, which is 3 pi. Okay, that's good. Let's see what's next. This means I screwed up, by the way. Let's see. Now we need to do 1, so we just have to perform 1. There's nothing you have to substitute into 1. So that's tau p is equal to mg x minus x hat. So when we sum these torques in F, so we're going to substitute C, D, and E into 2. When we sum these up, they're all in the same direction, right? So we have, what would that be? mgx is equal to, we don't have to worry about the x components anymore. We just have an x component thing. The square root of 3 over pi, which is common. 2 minus 1/2. All right, we can handle that. And then we have mgr. So that's going to mean that x is equal to the square root of 3 over, or 3 square root of 3 over 2 pi, right, because 2 minus 1/2 is 3/2, times r. Okay, so that's perfectly reasonable. That's an answer. It's got a bunch of numbers in front of an r. I'm good with that. So like I said, there's this 3 here, because I screwed up here. There should be a 2 there. Oops. Okay. So let's see. What else do we have? We have to see about the symbols in this one. That's not hard because we only have one symbol. That's the radius, and that's right there and right there. So it's okay that way. Gotta mark this up with red pen. Why it's delayed, I don't know. Now we need dimensions. Well, what are the dimensions of x? Well, the dimensions of x are length. And over on this other side, the only thing that we have with dimensions is r. So what are the dimensions of r? It's length. That's good. So the dimensions are fine. Again, 2 there, should be a 3 there. So what else do we have here that might be interesting? Does it make sense that if the radius increases, the position does? Well, yeah, it does, because this is basically geometrical, right? So if we had a bigger cylinder, then the centers of mass would be farther out, which means you'd have to push that box farther out to balance out the torques from those centers of mass. I mean, it's basically that easy, so that's not much to worry about. So again, the concerning thing here would be this. Probably you won't have to worry about that. Actually, at this point, we know you won't have to worry about that. So I do have an interesting problem for that, but I won't give it to you as much as I loved it. So now you have this nice little integral to do. That's fine. You did that in like lecture 2 was center of mass? Or was it lecture 3? Lecture 3. Lecture 3 was center of mass. So you've been doing this now for about 4 months almost. So maybe just 3 months. So you are, an expert at doing these integrals. Now we've done the torque, right? We've used rotational equilibrium here. So that was the thing that I really wanted to get out of this. And we've done several torque cross products, which is the reason why I keep hitting you with things like cross products over and over, is because it makes these things a lot easier if you know how to do the cross product. So it's not a big deal for this one. For the 2M wedge, for the wedge on the left-hand side, that it's not too big a deal, right? You can usually figure out that torque fairly readily, right? It's 2mgy. Once you start throwing angles in there, at some point you have to figure out, well, what is the right thing? Now people say, well, you use the perpendicular distance, right? Distance perpendicular to the force here. So then you have to figure out, well, where's this? Where's that? Where's the other thing? It just comes out of the math. So if you just learn the math, then everything's fine. You just have to be a little careful. If you have to sit around thinking about it, then you have a problem. And the biggest problem is the perpendicular distance is a lie, right? There's no such thing as a perpendicular distance, right? It's a perpendicular component to the force, but what you care about is the thing that makes it a torque is that it's the perpendicular component of the force to the pivot point, right? So the pivot's here, that's a real spot. The point of application's over here, right? That's a real spot. Your force is over here, you're pushing down this way. That's real, right? Those are all real things, right? And it's the component of this that's perpendicular to this. This is what you care about. You care about the perpendicular force, not the stupid perpendicular distance. Whoever invented that was just looking for a simple way to do some problems. And for some problems, it's easy and it just sort of washes out, right? You just look at it and you say, wow, that was easy, right? For some other problems, it doesn't do that at all, okay? For some other problems, it'll just completely break you, right? Trying to figure out what that perpendicular distance is or whatever. And just being careful in setting up your vectors and doing vector addition and subtraction and stuff like that, nice simple operations, they save you a lot of work. All right, so that was my fun with cutting up a cylinder. I hope you have some fun with the problem I'm going to give you. All right, bye now.